Today's speaker is Twesh Upadhyaya. Twesh is a PhD student and the Lanshos Graduate Fellow in Professor Nicole Younger-Halpin's group at the University of Maryland. Twesh has a series of papers on quantum key distribution, and he has also worked on quantum thermodynamics. Twesh is an author of the big review on the effects of quantum noncommutation on thermodynamic principles that was just published in Nature Reviews. Today, Twesh will be telling us about how noncommutation affects entropic quantities. So with that, Twesh, thank you very much for joining us, and the virtual floor is yours.
Thank you, David, for the kind introduction and for the opportunity to speak at the seminar. So today I'll be talking about our recent work on how transport of different quantities is modified in the presence of non-Abelian symmetry, and how, in particular, this affects what we commonly study as entropy production in thermodynamics. And this is the archive link to our paper. So a very common scenario across physics, across other fields very broadly, is two systems which exchange conserved quantities. And we consider the sort of scenario where these quantities are conserved globally, so the amount between the two systems together stays the same, but the quantity may flow back and forth between the two systems. And so, sort of echoing the nomenclature of electric charge, which is conserved, we call these quantities charges. So here we have two systems, A and B, and they're going to be exchanging some quantities. A classic example would be an ice cube melting in water. There, the exchanged quantity is heat, which leaves the water and enters the ice cube. That's a very simple classical example. A more quantum example, and something not involving heat, would be two qubits exchanging spin with one another. In this case, we could set up the interaction so that the amount of spin in total between the two qubits in the x, y, and z directions is conserved, but it could be shuttled back and forth between the two spins. In these sorts of setups, it's very typical to assume both systems start in thermal states, though at different temperatures or chemical potentials. So a sort of model for this is that the systems were in contact with some bath, they thermalized, and then at time t=0, we remove them from the bath and let them interact with each other.
Sorry, Twesh, I have a quick question here that I got in the chat. So someone asks, what is the thermal state if you're not commuting with the bath?
That's a great question, and I'd say we'll answer it in a couple slides.
Okay, thank you.
Yeah. So in this scenario, there's an entropy production, right? So ice cubes melt in water, they don't spontaneously refreeze, it's an irreversible process. And quantifying this entropy production is something that's been studied fairly extensively for classical systems, as well as for quantum systems with commuting charges. So that by that I mean all of these things that are being exchanged are represented by observables that commute with another. So for example, energy and particle number corresponding to the grand canonical ensemble. The key question we ask is, well, what happens when the charges don't commute with each other? Well, sort of generically, we would expect some sort of new phenomenon because we have seen it modify a lot of results in other areas of thermodynamics. So just as a brief sampler, it's led to reconsidering some derivations of the thermal equilibrium state. So to the question that was just raised in chat, what is the thermal state when you have non-commuting charges? It leads to modifications in the eigenstate thermalization hypothesis, which tells us about how quantum systems can thermalize even though the evolution is unitary and seemingly reversible. And finally, the entropy production has been studied in just the linear response regime, and it was found that actually non-commutation reduces the entropy production. So just to be super clear about the language, when I say commuting case, I mean all of our charges commute with one another. And by non-commuting case, I mean there's at least one pair of charges in the set, which the two charges don't commute with each other. Before we get into the nitty-gritty details of the talk, I wanted to just give a high-level takeaway of what we find. And our starting point is to say, well, in the commuting case, which is well studied, there's one sort of well-accepted definition of the stochastic entropy production. And what I mean by stochastic will become clearer a little bit later on. And this single definition can be expressed via three equivalent formulas. So to talk about the non-commuting case, we make some very minimal adaptations to these formulas that still satisfy a number of sanity checks. And yet we find, surprisingly, that these three formulae are actually no longer equal. They no longer just correspond to different ways of writing down the same single definition. And indeed, each formula highlights different ways in which this non-commutation is actually going to impact transport and entropy production. So for today's talk, I'm just going to go over a little bit more of the background and just a little bit of the relevant math. We'll talk about stochasticity and quasi-probabilities. So if you haven't heard about quasi-probabilities, don't worry, we'll go through them. But the sort of one-liner is they're almost probabilities. So they have some of the properties of a probability distribution, for example, being normalized, but they lack all of the properties. So for example, they can have real, negative real, or even complex elements. And finally, we'll do an analysis of these three entropy production definitions that we found, which we've dubbed the charge, surprisal, and trajectory definitions for reasons that will become clear as we go through the talk. So to get into the setup now with a little bit more detail, we have our two quantum systems, A and B, and we're assuming these are two copies of the same system, so they have identical Hilbert spaces. They're going to be exchanging these charges Q alpha. Here, alpha is just an index from 1 through C, so there's C different charges. And this exchange is mediated by a unitary U. So the U acts on the global system AB. We're going to assume the systems start off in thermal states. And now to answer the question that was raised in chat, what does the thermal state look like when you have multiple non-commuting charges? Well, it actually looks sort of very similar to what you would normally have even in the commuting case. There's a partition function normalization, that's not so interesting, but the exponential simply has each of the charges in a linear combination weighted by a generalized inverse temperature. So in the case that we're maybe more familiar with, the grand canonical ensemble would have the Hamiltonian, so for energy, and the particle number operator for particle number in the exponent, weighted by the temperature and a combination of the temperature and chemical potential. And here we see that even in the non-commuting case, the form of this thermal state, sometimes dubbed this non-Abelian thermal state, actually generalizes very, very straightforwardly. And there's a number of ways to see this. Maybe one of the most direct is some form of a max entropy argument, where just the linearity of the exponent just means that when we take matrix logarithms, we just pull out whatever's in the exponent. And so the non-commutation somehow doesn't play a role. So that's sort of just one reason why it's reasonable to understand that even though there's non-commutation, the thermal state form is just a simple linear combination in the exponent.
So there is a question here, Twesh.
Mm-hmm.
Someone is asking, is QA or Q alpha the Hamiltonian that describes the energy of the system rho A, or the Hamiltonian that drives the unitary that evolves an interaction between A and B?
Okay, great question. The answer is the former. So Q alpha is an observable just on system A or just on system B. And in the case where the Q is energy, we would actually have three different components. So we would have HA, and then we would have HB, which are the sort of same operator acting on the two different Hilbert spaces. And on top of that, we would have an H int, which is implicitly defined by this unitary U acting on the global system. So the initial state is a simple tensor product of these thermal, non-Abelian thermal states. And it evolves unitarily to some final state rho f. But what we really want to discuss is this scenario of charge transport. So it being conserved globally and transported locally. And for that sort of to make sense, we can't have charge just popping up out of nowhere. So what we need to enforce is that our unitary is actually conserving the total amount of charge. In other words, it commutes with the total charge. So we here take, Q alpha on A. So implicitly, there's like a tensor identity B plus identity on A tensored with the charge on system B. And this commutator should be 0 for all of the charges over all the alpha. And we'll see this pop up a little bit later, but just kind of want to flash that we'll think about each charge's eigendecomposition. So it'll have eigenvalues lambda and projectors onto the subspace pi. And what we're going to assume is that each pi is actually rank 1. So all of the charges are non-degenerate. We're ready to move on now to what we mean by a stochastic description. Because this unitary evolution that we've mentioned is deterministic, and the kind of very common way to go to a stochastic picture in the quantum setting is by introducing measurements. To motivate this, let's consider a simple scenario. So suppose energy were the only charge at play. So Q alpha is just equal to the Hamiltonian, and there's only one Q alpha. Here is a specific protocol we could do. First, before doing any unitary evolution, we actually measure both our systems, A and B, in this energy eigenbasis. And let's call the outcomes EIA and EIB. Then we evolve unitarily, as usual. But at the end, we again do a measurement in the energy eigenbasis, and here we call the outcomes EFA and EFB. This is kind of a prototypical scheme across quantum thermodynamics, and it's known as the two-point measurement scheme, or TPM. We can describe these measurement outcomes as a probability distribution. And we can actually think about the system as having undergone a trajectory. By that, I mean, after the first measurement, the system actually starts off in a tensor product of eigenstates, IA, IB. And after the final measurement, it ends up in a different eigenstate. So it's sort of like a discrete two-step trajectory that the system has taken. And if we had multiple charges, so not just energy anymore, we could do something very similar where we measure in the basis of one charge, then the next charge, and so on, do a unitary evolution, and finally measure all the charges again. So what we would get in that case is a longer system trajectory where we're indexing all of the outcomes of the measurement. So for charge 1, we index the outcome of which eigenspace we ended up in for both systems A and B. And after the unitary evolution, we do the same for charges 1 through C, except we call the index F instead of I, just to distinguish initial and final. So because the notation is already getting a little bit messy, there's a lot of indices to keep track of, just for simplicity, what I'm going to do is not explicitly write out the system index anymore. So here, when you see I1 on the right-hand side, this is just a shorthand for the composite index I1A and I1B. And same for all of the other indices. So that's just to wrap up, simplify the notation. But anytime we see an index like FC, what that means is it indexes the outcomes of the measurements after unitary evolution, so final, of charge C, so a measurement in the basis of charge QC, on both systems A and B.
So there's another question here, Twesh. So the person is saying, I think I follow, but could you explain if the E's, I guess these are the capital E's, have to be projectors onto states, or if they can be general, I guess general POVMs is what's meant.
Yeah, it's a good question. So right now, I've just sort of mentioned in the previous slide, we have the assumption that the charges are non-degenerate. So corresponding to, let's say, EIA, the eigenspace is just rank 1, and so it's just represented by a projector. We actually didn't consider the more general case of a POVM, but I think what our sort of approach is to say whatever the observable is, we can always break it down using the eigen decomposition. So we're guaranteed to get projectors. And now the only question is, are they degenerate or non-degenerate? So I would say, corresponding to EIA, it'll always be a projector, but it may sometimes be rank greater than 1, although that's not the case that we really investigated. Okay. So I've just described a very simple measurement scheme, this 2-point measurement scheme, but it's actually fairly unsatisfactory for our purposes. Why? Well, specifically when charges no longer commute with each other, doing these strong measurements is actually really going to disturb not only the initial state, but also subsequent measurements, which are going to be made in different non-commuting bases. So intuitively, one resolution to this might be to say, well, if strong measurements are giving us a lot of disturbance, why not weaken the measurement? Weak measurements will indeed disturb the system less, but this comes at the price of extracting less information. So just a kind of very high-level overview of what is a weak measurement in case you haven't seen it before. Well, we can think of any measurement, physically in the lab as being implemented by taking our quantum system, coupling it to a measurement apparatus, and then performing some sort of classical readout on the measurement apparatus. So for example, looking at the pointer of a device, collapsing its superposition, getting a single outcome. How strongly we couple the system and apparatus actually determines the strength of the measurement. So for example, we could not couple the system apparatus at all. That would be no measurement. And in another limit, we could allow the system and apparatus to evolve for a certain amount of time under, let's say, some interaction Hamiltonian, then measure the apparatus and implement a strong measurement. A weak measurement is kind of interpolating between those two cases where, let's say, we have the same interaction Hamiltonian. We just don't let the system and apparatus interact together for that long. So they develop some correlation, but not as strongly as they would when doing a strong measurement. So when the system and apparatus are only weakly coupled and we do a strong measurement, a strong readout on the measurement apparatus, the effective back action on the system is reduced, but so is the information that we get out. We've discussed probabilities in the context of the 2-point measurement scheme, where we're doing these projective measurements. And indeed, probabilities are a very natural language to describe strong measurements. For weak measurements, quasi-probabilities are a very natural language to talk about the resulting statistics. So I want to get into a little bit more of the math now of what our quasi-probabilities will look like. To do that, let's actually go back to the 2-point measurement scheme for a moment and think about how we would write down the probability distribution for this trajectory. We start with our initial state rho. And the first measurement, we simply put in the projectors for charge 1, followed up by the measurement of all the charges, so up to charge C. This is then followed by the unitary evolution that we perform. And finally, measurements of all the C charges again, this time going from charge C all the way back to charge 1. So this is simply a probability distribution with a lot of these projectors written out. Now, what does the corresponding quasi-probability look like for the weak measurement scheme? Well, it's actually really similar, and it should be read off in much the same way. We start with a state rho, then measure charges 1 through C, perform unitary evolution, and measure charges C through 1. And it's actually exactly the same as the strong measurement scheme probability. We've really just gotten rid of all of these projectors on the right-hand side. So in the commuting case, just as a sanity check, this quasi-probability is indeed equal to the probability. And just sort of a rough motivation for that is that when everything sort of commutes, the initial state is also diagonal, and all these projectors can be commuted through one another and cycled around the trace to kind of recreate this probability P. But in general, in the non-commuting case, this quasi-probability can be negative. It can even have complex elements. And so we sort of broaden our interpretation a little bit, where before we had a system following these trajectories from a set of initial eigenstates to final eigenstates, and they were weighted by probabilities. Now we really want to think of these trajectories as being weighted by quasi-probabilities. So not unlike, say, a path integral formalism, where different trajectories take complex, not necessarily real weights. The kind of specific name for this quasi-probability is an extended Kirkwood-Dirac. And so some of the properties that it has that are nice is that it normalizes to 1. So if we sum over all the indices, then, let's look at a particular projector, say pi 1. Because this is a complete basis, since we got it from the eigendecomposition of the observable, which was non-degenerate, we sum over this, it just becomes identity. And so we get a whole bunch of identities, the U and U dagger cancel, and we're left with trace of rho, which is 1. It also recovers the correct marginals, by which I mean, if we were to just measure one charge, what would the outcomes be, the distribution of the various eigenvalues? Well, again, just based on the same thing I just said, when you sum over any one index, that projector, all these projectors sum to identity and they go away. So for example, if we sum over all the indices except I1, we're just left with the trace of rho I1. And similarly, we would just be left with trace of rho IC. And we can contrast that with what happens in the regular probability. Here, if we were to sum over all indices I1, rho is actually not left unscathed. Instead, it becomes dephased, because what we've written down is exactly the dephasing channel. We're taking rho, and we're kicking off any elements that are not diagonal in the I1 basis. So what that means is if we were to do a measurement of charge C after that, it'll actually be different than what it would have been just on the original undephased state rho. So it's kind of a very nice property that this Kirkwood-Dirac quasi-probability has. Some ways the sort of price we pay for this is that it may take actually non-real value. So it's not just a simple probability distribution. So finally, we can talk a little bit now about stochastic entropy production, now that we've introduced this sort of probabilistic and quasi-probabilistic framework. Conventionally, so in the classical case, in the case of quantum systems with commuting charges, stochastic entropy production is a random variable over a probability distribution, P. And what it quantifies is, well, when the system undergoes a specific trajectory, what is the entropy generated on that particular trajectory, so on that particular realization. What we're going to do, and you kind of see where this is going, is to instead consider sort of quasi-stochastic entropy productions, defined as random variables over the quasi-probability now, as opposed to the probability. And to kind of go back to what I was saying in the beginning of the talk, in the commuting case, and again, specifically for our setup, there's this single well-accepted definition of stochastic entropy production, which can be expressed via 3 different formulas. We're going to generalize these 3 formulas to accommodate quasi-probabilities. So earlier I mentioned saying we're going to have to adapt these formulas slightly to account for non-commutation, and it's precisely this step where we have to accommodate quasi-probabilities as opposed to just a probabilistic description. But even with these minimal alterations, we actually find that in the commuting case, these generalizations still all reduce to the same thing. And again, in the commuting case, even the quasi-probability is simply a probability. And so this all satisfies the usual sanity checks, agrees with what we know in the commuting regime. But in the non-commuting case, the three formulae are actually no longer equal, and each is going to teach us something interesting. And we're almost there to the kind of exciting new results. But one last thing I want to do is just show what the stochastic entropy production looks like in the two-point measurement scheme. So just to kind of remind ourselves, what we had before, we're going to call the forward protocol. It was to prepare the state rho, measure the energies, and assign these to the initial indices, so IA and IB. Do unitary evolution and measure the energies again. But we can also consider a reverse protocol, and this is one very common way in which the stochastic entropy production is defined. Here we prepare the same initial state, but when we measure energies the first time, we actually assign the outcomes to these final indices. We evolve backwards in time, so using U dagger instead of U. And finally, we measure the energies again, but we assign the outcomes to the initial indices this time. The stochastic entropy production sigma is defined as the log ratio of this forward and reverse probability. We can then break it down a little bit into the probability of sampling a certain eigenvalue from the initial state and a conditional probability based on the evolution. And the details aren't critical, but what happens is the terms corresponding to unitary evolution actually cancel out, and we're left with simply a log ratio of initial state sampling probabilities, which, because of the sort of nice structure with the exponential, simplify considerably into these combination of betas, so inverse temperatures, and energies, so eigenvalues. So really the takeaway from this that I want you guys to keep in mind is these three different expressions. The one on the first line, where we have a log ratio of a forward and reverse process. The second to last line, where we have the logarithm of just initial state measurement probabilities. And finally, the last expression, where we have eigenvalues weighted by inverse temperatures. Okay, so this might actually be a good place to stop and ask if there's any questions before I get into our main results.
I don't see any questions in the chat, so this is crystal clear, it seems.
Okay, great. Then I'll keep plugging on through. So I'm not going to present our three definitions or three flavors, if you will.
There is a question now.
There's a question? Okay.
Yeah. So someone asks, so in this system, do you need to be able to reverse time? That is, do you need to be able to apply the inverse of the unitary that drives the system? And can you always do that in experimental scenarios?
Mm-hmm. That's actually a very nice question. So the answer would be no, you don't always need to be able to implement UDagger. And the reason is we can actually look at one of these sort of matrix elements. So let's say here in the denominator. And instead of thinking about UDagger, what I could instead have done is actually introduce the time reversal operator and have that acting sort of in between the U and F and U and I. And basically then, instead of thinking of implementing UDagger, I can instead think about my experimental capability as being preparing a time reversed state and then just implementing the same U. So it sort of works out because we're taking all of these products that you can equivalently think about it as being F evolved by UDagger and then projected onto I. But from a sort of physical standpoint, the way to really do this would be to think about preparing a time reversed state and then performing unitary evolution. And that would be kind of how you actually do this in the lab.
Okay, I think that makes sense. Thank you.
Yeah, that's a great question. So I'm going to present our three formulas, or three flavors, if you will, of stochastic entropy production. We call the charge, surprisal, and trajectory. And again, just kind of drive this home. So these are different definitions, and in the non-commuting case, they aren't equal, but each is really highlighting some interesting way in which this non-commutation is impacting the transport of these charges. And each definition satisfies a number of sanity checks, so we kind of deem them as very reasonable candidates for entropy production. The two main takeaways we're going to have, these kind of calculations that we'll do, are going to be averages and fluctuation theorems. And if you don't know what a fluctuation theorem is, don't worry, we'll get into it. But from here on out, we're going to be doing a lot of averages with these angled brackets. So whenever you see those, that always means an average taken with respect to the quasi-probability. So just like a usual average, except we don't have a probability there, but we have a quasi-probability, sum over all of the indices of whatever's inside those brackets, multiplied by the quasi-probability element at those indices. So here is our first definition, the charge definition. And I hope you see why I wanted you to keep in mind the three steps in that 2-point measurement entropy derivation. So this really corresponds to that last line. We have eigenvalues weighted by inverse temperatures beta. And this definition really captures entropy as an extensive thermodynamic variable. And we'll see a little bit more about that in later slides. The next definition is the surprisal definition, and this really connects to entropy's information-theoretic roots as a measure of uncertainty. Here we have just the log ratio of measurements only done on the initial state. So, for example, the denominator is the trace of rho with the projector in the basis of charge alpha, which is indexed with F alpha. It's indexed with F alpha, but again, this rho is the initial state. This is just a measurement on the initial state. We're just assigning it these F, or final indices. And this should remind you very much of the step in the 2-point measurement derivation. Just prior to these betas and E showing up, we had a log ratio of just the initial and final. We had a log ratio of measurements of the initial state indexed with initial and final indices. And finally, our third definition is the trajectory definition, which is really coming back to entropy as a quantifier of irreversibility. And again, just like we had in the TPM derivation at that very first line, so sort of working back through the various steps, we have a log ratio of a forward and reverse process, except these are now quasi-probabilities. So for example, the forward quasi-probability is exactly what we've written down earlier, whereas the reverse one corresponds to a sort of reversed process, where now you can see the F-indexed projectors are hitting rho first. We're doing reverse time evolution because this U is on the right-hand side of rho, right? So it's like U dagger rho U. And we're measuring the initial charges last. So this corresponds to sort of a very natural notion of reversal. So just kind of keeping these in mind. So the log PF over PR, logs of initial state probabilities and the betas and lambdas, sort of just flash back to the TPM derivation, and again, point out the very, very strong analogy between the first line, so the trajectory definition up here, the surprisal definition, and finally the charge definition. So these are very, very closely related and inspired by these steps in the 2-point measurement simplification. Okay, let's talk a little bit more about the charge definition. Basically, by construction, the average that we get is very closely resembling these results from classical thermodynamics. So if we think back a little bit, we're familiar with this sort of fundamental relation of thermodynamics, dE equals TdS minus PdV plus mu dN, etc. And if we were to rearrange that a little bit, we can actually express ds in terms of the differential changes in other extensive quantities. That is essentially what we have here with just slightly different notation. Here, these delta betas show up because we have two systems. So there's a change in the, or a difference in the inverse temperatures. And the delta Q alpha is just like the differential dE in this classical thermodynamics formula. It's the change in the amount of that charge just on system A without lots of generality, because whatever leaves system A must go into system B by charge conservation. One nice feature of this formula is that it's actually always non-negative, and that can be seen by actually writing it as a relative entropy. So the quantum relative entropy, for those that haven't seen it before, is one way of measuring or quantifying the distinguishability between two states. And although it's not a metric, it has the property of being always non-negative. So just the relative entropy between the initial and final states captures this average form. Again, yeah, so it's the difference of betas. And right, so this is just a reminder to see the kind of classical thermodynamics formula in terms of dE, TdS, and how it, after some rearrangement, it's actually exactly resembles our formula, which is something that also shows up in quantum thermodynamics quite often. But the important thing to note is that actually this formula, this delta beta, delta Q, is valid for large flows, whereas the classical formula is for infinitesimal flows where the intensive quantities don't change. This is actually valid for a very large flow, where at the end, the system states are far from equilibrium. They don't necessarily have a well-defined temperature. And still, this formula, just based on the initial temperatures, is valid. Now, we'll talk about the fluctuation theorem. So what is a fluctuation theorem? Well, it's just going to be the average, not of the entropy production directly, but of the exponential e to the minus sigma. And so this is kind of closely related to like a moment generating function or cumulant generating functions. And typically, fluctuation theorems simply have a 1 on the right-hand side. So in many classical fluctuation theorems. What we find is some fluctuation theorems where the right-hand side is actually 1 plus quantum corrections. And this has some precedence in earlier work on quantum thermodynamics as well, kind of identifying these quantum corrections to fluctuation theorems. In our case, there's two corrections. We can sort of, I won't write out the explicit formula, but we can break down explicitly the correction into these two terms. The first one comes from the non-abelianity of the thermal state that we started off with, and specifically the fact that when I prepare this thermal state and the charges are non-commuting, the initial state can actually have coherences relative to the with respect to one of the charges bases. And that can only happen when the charges are non-commuting, because if everything commutes, everything can be simultaneously diagonalized, and the thermal state is also diagonal in that basis. So these coherences actually lead to corrections. And the second set of corrections comes from what we call non-conserving trajectories. So what are non-conserving trajectories? Well, these are going to be the sets of indices. So remember, a trajectory is just a set of indices, I1, I2, up to IC, and then FC, FC minus 1, all the way to F1. If any of those I and F pairs, so for any alpha, has satisfied this condition, so the eigenvalue corresponding to that charge Q alpha, summed up on the initial indices, so IA and IB, is not the same as the eigenvalue summed on the final indices, then we say that set of indices corresponds to a non-conserving trajectory. So, well, we don't normally think about this because in the commuting case, the quasi-probability, which is just a probability, is actually equal to 0 on any of these non-conserving trajectories. So just, what am I saying? We have a distribution. It has elements over a whole swath of indices, specifically on those index sets where this property is satisfied. So there's this inequality. On those index sets, the distribution is 0. So those trajectories don't matter. They have no weight. However, in the non-commuting case, the quasi-probability actually can have non-zero weight on these non-conserving trajectories. And in some sense, we can think of this as a sort of violation of kind of a detailed charge conservation. So to be really clear here, even in the non-commuting case, we have charge conservation in the sense that I described earlier. The unitary commutes with the total charge. The total charge in the system as an observable is conserved. It doesn't change. However, when we're kind of introduced to stochastic picture through weak measurements and this quasi-probabilistic description, we actually find that in the sense that the system is following these individual trajectories, each trajectory individually we can think of as actually having violations of these charge conservation. However, when we take averages over indices and look at just observables, we do still have charge conservation. So that's why I sort of call this like a detailed charge conservation. It's at the stochastic level. But it's not to say that we don't have overall charge conservation. We still for sure have that in the non-commuting case. We're still imposing U commutes with the Q totals. And the connection I really like to draw here is to the path integral formalism and say something like the double slit experiment. So classically, we have just two trajectories. The particle goes to the left or the right slit. Whereas in the quantum case, we have all these additional trajectories, which are sort of classically forbidden. And yet the interference from these trajectories corresponds to observable effects, so interference patterns. In this case, something very similar. We have these classically forbidden trajectories, these non-conserving trajectories, but non-commutation, a very quantum effect, enables the system to explore these trajectories, and these corrections lead to observable effects in the fluctuation theorem. So our next definition is the surprisal definition. And here, the really interesting takeaway is in the average. So it's actually really similar to before. We have a relative entropy between the final state, but now instead of with respect to the initial state, it's actually with respect to the dephased initial state. So in particular, dephased in the basis of charge Q alpha. And there's this second component here, which actually comes in with a negative sign. And what that means is that this average can in fact be smaller than just the first term, but indeed even negative. And this was sort of interesting because typically in such a scenario where we've just taken two thermal states, brought them together and let them interact, we don't typically think of this as being a process that leads to negative entropy production. But what this definition is really sensitive to is these initial coherences I mentioned earlier. And this is sort of suggestive that these coherences are a resource that can be used to sort of simulate a reversal of times arrow or of generating negative entropy production. And sort of an interesting question that we want to look at in the future is, can we come up with an explicit protocol for extracting some amount of work from these initial coherences? And is it quantified well by our surprisal definition? And I won't spend too much time on it, but the fluctuation theorem also has this form of 1 plus a correction. In this case, the correction comes from coherences in this initial non-abelian thermal state relative to the Q alpha basis. And finally, we'll talk about the trajectory entropy production.
Sorry, Twesh, there's just a question here. Can you relate these to the Jarzynski equality?
Yes. So in the case where we have, so let's take a really simple case. If we just have one charge and it's the energy, all of our derivations and results reduce to Jarzynski-Wojcik's 2004 PRL paper. So in particular, this sort of derivation is exactly what is found there. So
okay,
because there's and just to be super clear, like what I'm referring to is in this 2004 paper is what's known as like this Jarzynski's like exchange fluctuation theorem. And there's also very closely related but slightly different results, which are fluctuation theorems involving work and free energy, and those involve just a single system with a control Hamiltonian. This exchange fluctuation theorem is for two systems which are interacting. Okay, so the trajectory definition here, the key takeaway is actually that the average entropy production can actually have an imaginary component which signals contextuality, which is a very kind of strong, provable form of non-classicality. So here we get the explicit form just for a simple case where the global state is pure. So this is one area where I'm kind of going away from the assumption we've had all along that the initial state is this tensor product of a thermal state on system A and B. Here I'm assuming the initial state globally is pure, but the reduced state, so the marginals on system A and B, are still looking like a non-Abelian thermal state with the same temperatures beta. So the real part of this average is non-negative because it's now the sum of two relative entropies. And it's sort of interesting because it involves this dephasing in the basis of charge 1 and also forward and reverse time evolution. And this imaginary component is the difference of two weak value phases. So I won't get it too much into what a weak value is, but please feel free to ask if you have questions. But basically, how you can think about what's going on here is, recall that our trajectory definition was formulated in terms of a forward and reverse process. And we can think about a very closely related scenario where we actually make those weak measurements that we were talking about back to strong measurements. So in this case, the system starts off in some pure state because we assumed it's pure. And after each measurement and the in-between unitary evolution, the system collapses into some eigenstate. So in other words, the system is tracing a path through state space from one pure state to another. And it's going to trace a different path when we implement the reverse process. Over these two different processes, sort of visualized here, the system is going to accumulate some geometric phase. And what this definition is capturing is that the geometric phase that accumulates in the forward and reverse process may not exactly cancel out. And so this irreversibility in state space is captured by the imaginary part of the average entropy production. And it's kind of nice. The fluctuation theorem in this case is just really simple. There's no corrections. It's just always equal to 1, which you can kind of see at a glance because we defined this trajectory definition as the log ratio of the forward and reverse quasi-probabilities. So things work out very nicely, just as for the 2-point measurement scheme. Okay, so just to summarize, we presented these 3 formulas for stochastic entropy production, which, although equal in the commuting case, are actually inequivalent in the non-commuting case. And each formula captures different aspects of how non-commuting charges alter the entropy production. The charge definition shows us that non-conserving trajectories, these sort of classically forbidden trajectories, underlie corrections to a fluctuation theorem. From the surprisal definition, we glean that initial coherences from the non-abelianity of the initial state can actually make the entropy production negative. And finally, in the trajectory definition, we see that the non-real entropy production average signals contextuality. So some of the future work we want to study are how degeneracies affect it. So I mentioned a few times that we've assumed the charges are non-degenerate. Also symmetrizing. So, I wrote down a specific order of measurements, charges 1 through C, unitary evolution, then measuring charges C through 1. But what about considering different measurement orders, or in fact symmetrizing over all possible orderings? And finally, exploring applications to, for example, quantum engines, and seeing whether these coherences can be exploited as a resource to improve the efficiency of the engine, and whether that's quantified well by our entropy production definitions. So thank you everyone for listening, and please if you have any questions or comments. I'll just put up the links again.
Thank you, Twesh, for a really nice and exciting talk. I can see we have one question, which is someone asks if you could elaborate what the meaning of negative entropy is.
Absolutely, it's a great question. So, I think the best way to think about this is to think in sort of terms of resources. So, there's a very nice paper by Jennings and Rudolph where they talk about entanglement and the error of time. And there they basically consider, a hot and a cold quantum system, in so much as the reduced states are thermal states that are hot and cold, but where the global state is actually entangled between the two systems. And what they show is, in fact, at least for some amount of time, heat flows in the wrong direction. So it flows from cold to hot. And so in that sense, there's negative entropy production. But this is sort of a function of a very particular initial state. So the sort of second law is always valid, but when you write it down, it's important to account for sort of what are these different sources of entropy in my setup, and what are the kind of resources at play. So if I just have two systems, uncorrelated, unentangled, sure, heat will flow in the right direction. But if I have entanglement, this sort of resource that I can burn up, then I can temporarily reduce my entropy production. The same way I can do work and reduce the entropy of a system for some time. But you pay a price globally. So either in whatever process generated that entanglement in the first place, or in the work you have to do, or in the work you would have to do to generate that entanglement, there's going to be more entropy production than whatever you kind of save in that later interaction. So globally, entropy always increases, but negative entropy production is just one way to talk about how can I have some resource or energy in my system. And there's actually a very direct analogy between the Jennings-Rudolph paper and what I mentioned. If you look at this formula and you were to replace this dephasing of rho with a decorrelating, by which I mean you take rho and you take it to its two marginals. So whatever rho it, let's call it sigma. Let's say the state is sigma, which is a bipartite state AB. You take sigma AB to the state sigma A, tensor sigma B. So you remove any correlations between the two systems. If you make that replacement on the dephased state both times with a decorrelated state, you actually exactly get back the results that they had. So their notion of entropy production, which is this delta beta delta Q1, and the fact that it's negative because of a difference in the initial state between its the initial entangled state and its decorrelated state. So sort of one way what we're seeing here is, well, actually, even when your initial state doesn't have entanglement or even correlation, it's just a tensor product state, still these coherences, which are a kind of only seen in the thermal non-commuting state, can actually have the same effect of being this resource that you can exploit to drive heat in the wrong direction, reduce entropy production temporarily, though of course, in the universe at large, it'll always be going up.
Okay, thank you. We have a question from Chris Long. He's saying, how do you consolidate imaginary entropy with classical entropy, which is manifestly real?
Mm-hmm. I mean, I think it's a fair question. I think what's really important, I would sort of say sort of two things. One is, what's clear is that there's a lot of things going on in sort of scenario, a lot of quantum effects, and probably no one number, like no single quantifier is really sufficient to capture all of the different effects. So as we see, we have these different definitions that quantify different interesting concepts. And in a way, calling it the imaginary part is really just wrapping up two real numbers. So in some sense, I could present this as like a vector of two real valued numbers and say these are two pieces, right? But I think that's it's a little bit of a cop out, but I think what's really crucial, right, is to say, okay, you claim there's an imaginary part, but what does it mean? What does it physically connect back to? And there I would really just emphasize again the story that this imaginary component really ties very is let's say spiritually very similar to classical entropy production in that it's capturing something about irreversibility. Classically, we think about the system going through its state spaces and the spreading of its probability distribution. But as we know, quantum states don't live in the same state space. They live in Hilbert spaces. Complex numbers are very important. And so I think it's very reasonable that when we start talking about trajectories through state space and the irreversibility of such trajectories, that having complex numbers pop up is fairly benign in that context. So kind of my one-sided answer would be, it comes down to irreversibilities of trajectories in state space, and we know quantum state spaces have complex numbers, so I think it's kind of reasonable and reconciles with how we describe classical systems, which we can just do with real numbers.
Thanks. Hugo?
Yes, I have a quick question. So at the end, you mentioned some of the applications, and you mentioned making more efficient quantum engines as an example. Could you elaborate on what kind of problems we could solve with this, or where you'd see an advantage in using this to create more efficient quantum engines?
Mm-hmm. And sort of just a high-level idea I had in mind is, so to have a quantum engine where instead of operating between just say reservoirs of heat, you have access to multiple reservoirs of non-commuting observables, where you could just take any one of them. So let's say like a system had access to like X and Y spin bands at high and low chemical potential. If you just use just the X ones, you probably get very analogous results to just a flow of energy, or you're just using a single flow. But what happens if you try to use both reservoirs? So you can kind of let your engine interact and thermalize not just to the thermal state of a single charge, but to a non-abelian thermal state, run a cycle, dump your excess and reinitialize it. So basically just to study whether having these non-commuting bads as opposed to commuting bads can give you some like advantage that you can express in terms of the norm of a commutator or something like that.
Right. But would this be used for computation? Are you somehow extracting information out of this process, or really
I was just thinking on like as a nanoscale heat engine, what would a nanoscale like non-commuting engine look like, and could it be more efficient? But I think like the practical benefits maybe are questionable, because the amount of output from any small quantum engine is really minuscule. So
sure. I totally respect studying the foundations of science for the sake of studying the foundations. I was just wondering if, because like the heat engine, this must be on such a small scale. Even if you're pumping the efficiency beyond a classical limit, are you really cooling something to any degree that are you getting any practical advantage in any way?
Right. Possibly there's some advantage if people can really engineer some sort of like small like nano machines at that level, or understanding maybe the behavior of small machines that nature has built for us, like some molecular pumps and cells, and studying how they behave.
Yeah, cool. All right, thanks.
Yeah.
Okay, Twesh, thank you so much for presenting and answering all our many questions.
Yeah, thanks for the seminar. Yeah, great to be here.
And yeah, send our regards to all the people in Maryland, and hope to see you soon.
Will do. Yeah.
Visit the group if you ever come to the UK.
Absolutely, will do. Thanks.